Hello, everyone, and welcome to Type 1 Improper Integrals. In this section, what we want to do is look at definite integrals where the interval of integration is of infinite length. So when you have such a scenario, this is what we're going to refer as a Type 1 Improper Integral. The only way to truly understand Type 1 improper integrals is by understanding them visually. So let's look at the two cases of improper integral of Type 1. In the first case, we have a function f of x, and that function is defined from a all the way up to infinity. And informally speaking, what we're trying to compute here is the area under f from a all the way up to infinity. So here we go. Boom. The area of this gray region is what we're trying to get to. But is that even possible? One thing that is absolutely crucial to understand at this point is that we know how to compute definite integral for functions over closed interval. And when we have a primitive for a function and we're trying to compute a definite integral over a closed interval, y a pas de problème là. You just have to use the first fundamental theorem of calculus, big F of B minus big F of A, and then you get your value. But here, the problem is that we cannot use initially the first fundamental theorem of calculus because our interval is infinitely many long, and the first theorem of calculus cannot help us yet. But there is a way. To represent this gray region, we can use the notation of integrals. So the area of the gray region would be the integral from a to infinity. But again here, I need to stress the fact that the reason why this is called an improper integral, it's because one of the bound is infinite. In this case, plus infinity. The upper bound is plus infinity. So we can only use the first fundamental theorem of calculus if we're trying to compute a definite integral for a function defined over a closed interval AB, and it's not the case here. But there is a way to go around this problem. What you do is you pick a value, let's call it t, that is very, very, very large, far, far, far away from A, and you first compute the definite integral from A to T. So here we go from A, boom, and we stop at some value T, and we want to compute the definite integral from A to T for f of x dx. And here there's no problem. There's no problem, okay, because my function f over A to T, that's a function that is well defined over a closed interval. So we know how to compute this. If we have a primitive for small f, let's call it big F, we know this is big F of t minus big F at A. So there is a way to compute that region. So here, just to illustrate what we can compute first, I decided just to represent this region in purple. Boom. Okay, so here's my region, and I know how to compute this. But of course, the area of the purple region is not the same as the area of the gray region. We're missing a little chunk. So how can we get there? How can we go from this purple region, which is the definite integral from A to T, to the improper integral from A to infinity? Well, what you do is you just study the behavior of this purple region as t gets larger and larger. And how can you study something where a number gets larger and larger? By using a limit. Oh yeah. So we're trying to compute the area under f from A to infinity for a function f of x dx. But we can't initially because of the infinite bound. So the first thing you do is you get rid of that bad bound. So you're going to integrate between A and T, where T is some very large number. And here, computing the definite integral between A and T, there's no problem. We have a lot of tools to compute this. In particular, you can use the first fundamental theorem of calculus. If you find a primitive for small f, you're in business. But of course, this definite integral is not exactly what we want. So now what we want to do is study the behavior of the area of this purple region as t gets larger and larger. So what you're going to do, you're just going to push this quantity as t goes to infinity. And then there's two scenarios. Either this limit will go nowhere, and then in that case, we're going to say that this improper integral diverges. But if the value of this limit exists, we're going to say that the integral between a to infinity of f of x dx converges to the value of that limit. In the second case, we have now a function that is defined from minus infinity to the point a, and we're trying to find a way to compute the integral from minus infinity to a. So visually, this is the zone that we're looking for, the gray zone here. Boom. Okay, so this is the definite integral from minus infinity all the way up to a. So using the integral notation, so we can write this as the following. Boom. Okay, so the integral from minus infinity to a. But again, we're trying to do something that is improper because the function is not just set up over a closed interval. So using the same idea as before, we cannot start from minus infinity, but we can start at a value t that is very large, negatively speaking. And we're going to call that value again equal to t, and we're going to first compute the definite integral from t to a. So using the integral notation, this is what we're trying to do now. So here we go. Poof. So we want to do some integration from t to a. So if I want to color this region in purple now, I could do it the following way. So here we go. Boom. Okay, so I can color it in purple. So computing the area of the purple region is not a problem. And the reason why it's not a problem, it's because now f is simply over a closed interval, and we have tools to compute the area of that region, in particular, the first fundamental theorem of calculus. So we're trying to compute the integral from minus infinity to a of a function f of x dx. Again, the problem with this problem is the minus infinity bound. So what you do is you first compute the definite integral from t to a of the function f of x with respect to x. And now this is good because this is a definite integral. So we have tools to compute this, in particular, the first fundamental theorem of calculus. So we have a lot of tools. But of course, the area of the purple region is not exactly the same as the area of the gray region. So in order to get to that value, we need to push t to minus infinity. And the way you do this is by computing it using a limit. So the integral from minus infinity to a for a function f of x dx is by definition the limit as t goes to minus infinity of the definite integral from t to a for the function f of x with respect to x. And again, if this limit does not exist, we're going to say that the integral from minus infinity to a for the function f of x with respect to x diverges. If this limit exists, so if it goes to a value, we're going to say that the integral from minus infinity to a for that function f of x with respect to x converges to that value. Again, for the two visual cases, it's absolutely crucial to spend some time with these pictures, because if you're trying to understand improper integration by reading the definition, or the integral from a to infinity of f of x dx is the limit as t goes to infinity of the integral of a to t of f of x dx, and the other one is the integral from minus infinity to a of f of x dx is the limit as t goes to minus infinity of the integral of t to a of f of x with respect to x, good fucking luck. You're not going to get anything out of that definition. Use a picture. Come up with your own definition. If you understand what's going on, you're going to match up the actual definition. And the best way to truly capture the essence behind the definition of this improper integral is with a picture. Honestly, all the examples are just going to summon things that we've seen before, which is computing primitives and computing limits. But really, what's new now is how do you set up these improper integral? And the best way to truly absorb this is using these little pictures. Anyways, got too excited there. So let's go and look at some examples. First example, let's compute the integral from 1 to infinity of 1 over x squared dx. From now on, every time you're computing an integral with bounds, even if the bounds are not infinity or minus infinity, you have to compute the domain of the function that you're trying to compute the integral, because this is the only way to truly check if there's any problem with your integral. So here in this case, 1 over x squared is defined everywhere but at 0. So poof, the domain of that function is everything but 0. Because we're trying to compute the integral from 1 to infinity, we don't have any issues with the domain, but we will at some point, okay? But not in this example. So here, the only problem with this problem is the infinite bound. So I have found an improper bound here, so I need to first define this correctly. So you need to get rid of this improper bound. So this improper integral from 1 to infinity will become the integral from 1 to t. So you replace the infinite bound by t, 1 over x squared dx, and then we're going to push t to infinity. And this is very important. That line in the solution is always going to give you most of the marks for an improper integral question, because this is truly the only new thing. Once you have this definition well written down, in this case, replacing the infinite bound by t and pushing t to infinity. So an improper integral is always a combination of a definite integral and a limit computation. Then the rest is really just summoning tools that we're already familiar with, which is definite integration and limit computation. So the first thing that you do once your improper integral is well defined as a combination of a definite integral and a limit is to compute the indefinite integral of your function. So you forget about the bounds, you forget about the fact that this is an improper integral. So first, let's just compute the indefinite integral of 1 over x squared dx. Poof. Here, this one is a basic indefinite integral. So the indefinite integral of 1 over x squared is minus 1 over x plus c. And because we know that we need to use a primitive if we want to use the first fundamental theorem of calculus, you just define one primitive, and the best one is always going to be the one where the c value is equal to 0. So poof, so my f of x, big F of x, is going to be minus 1 over x. The second step is to compute the definite integral of 1 over x squared between 1 to t. So here we go, poof. So we want the definite integral of the function 1 over x squared between 1 and t. And now, because we're over a closed interval, we can use the first fundamental theorem of calculus. And we know that this integral is going to be equal to, poof, big F at t minus big F at 1. And we know what f is, so we just evaluate big F at t, and we evaluate at 1, and we subtract the 2, poof, so you're going to get minus 1 over t minus 1 over 1. And it's really important in these questions to simplify this equation with respect to t, because we're going to push it using a limit. So here 1 simplified, this is 1 minus 1 over t. So that's my definite integral of 1 over x squared over the interval from 1 to t. And now the third step is to actually compute the limit of this definite integral. So poof, so we want to compute the integral from 1 to infinity of 1 over x squared dx. We know by definition, this is the limit as t goes to infinity of the integral of 1 to t of 1 over x squared dx. So that's the definition that we did initially. And now what we're going to do is we're going to replace this definite integral between 1 and t of 1 over x squared dx with what we just freshly computed. So we know it's 1 minus t. So now the definite integral is gone. We have a formula. It's 1 minus t. And now we're going to compute the limit of this as t goes to infinity. So here, just by plugging t by infinity, so by replacing t by infinity, you get 1 minus 1 over infinity. 1 over infinity is 0, so you're going to get 1. So you're getting a value. So the limit as t goes to infinity of the integral between 1 and t of 1 over x squared dx is equal to 1. So this means, as a conclusion here, this means that the original improper integral, boom, from 1 to infinity of 1 over x squared dx converges to 1. Let's review the steps together. So the first thing that you do when you're computing an improper integral is you first find the correct definition as a combination of a definite integral and a limit. This is the most important steps. On a test, half of the mark is for that part of the solution. Of course, the solution itself is way longer, but the most important part is, can you write the correct definition? Once this is done, the rest is just stuff from the past. The first step is to simply compute the indefinite integral. So you forget the bounds, you forget the limit, you just compute the indefinite integral. You find the family of antiderivative for your function, and then you just choose one. And of course, the best one to choose is always the one where c is equal to 0, and you call that function big F. Then the second step is to compute the definite integral that you have in your definition. And by using the first fundamental theorem of calculus and the f, the big F that you freshly define, you just compute your big F at your upper bound minus your lower bound. Clean this up a little bit because you're going to use it. And that's your second step. And then the third step is to use this freshly computed formula and then push it to the limit. In this case, we had to push it to infinity. And then by looking at the answer, if it goes to a number, you just say that your improper integral converges to that value. If it doesn't go to a number, you just say that it diverges. But those are the steps. And the only new step in this solution, the most crucial thing, the most important thing, is really the way you're going to get rid of the bad bound or get rid of the problem in general by using a correct combination of a definite integral and a limit. So an improper integral is a combination of a definite integral computation and a limit computation. So, all right, next example. Let's compute the integral from minus infinity to 0 of ex dx. So the first thing you do from now on, every time you compute an integral with bounds, you compute the domain of your integrand. Here the function is ex. Ex is defined everywhere, so the domain is everything. So the only issue we have with this integral is the lower bound being minus infinity. So that's our bad bound. So we need to get rid of this bad bound. So you do that by replacing minus infinity with t. So now we're going to compute the definite integral from t to 0 of ex dx. And then we're going to study this definite integral as t goes to minus infinity. So we're going to compute the limit as t goes to minus infinity of that definite integral from t to 0 ex dx. And again, this is the most important step in your solution, to have a good definition for your improper integral as a combination of a definite integral and a limit. The first step is to compute the indefinite integral of your question. So you forget about the limit, forget about the bounds. So here we go, boom. The integral of ex dx is equal to ex plus c. So if we are going to use only one primitive, might as well use big F of x equal to ex. The second step is to compute the definite integral from t to 0 of ex dx. So here we go. So boom. So, and here I'm going to use, of course, the fundamental theorem of calculus, the first one. So I know that this is going to be equal to big F at the upper bound, which is 0, minus big F at the lower bound, which is t. And now using my function freshly defined, I have e to the power 0 minus e to the power t. E to the 0, remember, it's just 1. So I have 1 minus e t. So that's my definite integral. And the last step is to summon back our good definition for our improper integral. So we know, boom, that the improper integral, so the integral from minus infinity to 0 ex dx, is equal to the limit as t goes to minus infinity of the definite integral from t to 0 of ex dx. Now I'm just going to use the formula that I've computed in step 2. So this limit will be the same as the limit as t goes to minus infinity of the formula freshly computed in step 2, 1 minus et. Now I'm just going to plug minus infinity in there. So I'm going to get 1 minus e to the power of minus infinity. E to the power of minus infinity is 0. So my limit is equal to 1. So this means that the integral from minus infinity to 0 of ex dx converges to 1. Next example, let's compute the integral from 2 to infinity of 1 over x ln of x dx. As usual, from now on, every time you're computing an integral with bounds, you need to compute the domain of your function. In this case, because of the logarithmic term, we know x needs to be strictly positive, and also because ln of x is at the denominator and because ln of 1 is 0, we need to kick 1 out from the domain. So this means that the domain of this function will be everything strictly bigger than 0, but we're going to exclude 1. Because we are integrating from 2 to infinity, the only problem with this problem is the infinite bound. So this means that this improper integral will be equal to the integral from 2 to t first of 1 over x ln of x dx, and then you're going to push t to infinity. So that's the correct definition for this improper integral. The first step is to compute the indefinite integral of 1 over x dx. So in this problem, here we go, boom, the indefinite integral of 1 over x ln of x dx is ln of the absolute value of ln of x plus c. You will need substitution here to find that family. And if you only need one primitive to use inside the first fundamental theorem of calculus, I'm going to use big F of x as ln of the absolute value of x. So by choosing c equal to 0. The second step is to compute, the definite integral from 2 to t of 1 over x ln of x dx. We know by the first fundamental theorem of calculus that this is going to be f of t minus f of 2. By using our function that we just freshly defined, we know that this is going to be equal to the ln of the absolute value of ln of t minus ln of the absolute value of ln of 2. And that's our equation for this definite integral. Now our final step is to compute the integral from 2 to infinity of 1 over x ln of x dx using the limit as t goes to infinity of the integral from 2 to t of 1 over x ln of x dx. So we know that now this limit will be equal to the limit as t goes to infinity of our formula that we freshly computed, ln of t with an absolute value minus ln of 2. The absolute value here is actually redundant because ln of 2 is a positive number. Now you just plug infinity in there, you get ln of infinity minus ln of 2. Ln of infinity is infinity, so you get ln of infinity minus ln of 2, which equals to infinity minus ln of 2. And that will be equal to infinity. Then the conclusion is the following. Boom. The integral from 2 to infinity of 1 over x ln of x dx diverges. All right, last example of this section. We want to compute the integral from 1 to infinity of 1 over x squared square root of 1 plus x squared dx. As usual, the first thing you do when you have an integral with bounds is you look at the domain of your function. Here, the only way this function can crash is if and only if x is equal to 0. So here we go, poof, the domain is everything but 0. Because we go from 1 to infinity, the only way this can be a problem is because of the bound that is infinity. So this will be equal to the integral from 1 to t. So the infinite bound is replaced by t of 1 over x squared square root of 1 plus x squared dx. And then we're going to study this definite integral as t goes to infinity. So that's the proper definition for this improper integral. First step, which is not an easy step in this question, is to compute the indefinite integral of 1 over x squared square root of 1 plus x squared. Actually, here you will need trigonometric substitution to find the family of antiderivative and then to define your primitive that you're going to use in this question. So here we go. Boom. So as an exercise, you can try it on your own, but a family of primitives for that function is minus the square root of 1 plus x squared over x plus c. And the big F I'm going to use is minus the square root of 1 plus x squared over x, where the c is simply set equal to 0. The second step is to compute the definite integral from 1 to t of 1 over x squared square root of 1 plus x squared dx. So by using the first fundamental term of calculus, here we go. Boom. Okay, so it's going to be equal to f at the upper bound, so f of t minus f at the lower bound. So f of t, I'm going to get minus the square root of 1 plus t squared over t minus, so same thing at 1. So be careful with signs here, minus 1 plus 1 squared, square rooted, all that over 1. And if you simplify everything, the minus minus will become a plus. I have the square root of 2 over 1. I'll put this one first just to make it more beautiful. So here we go, square root of 2 minus the square root of 1 plus t squared, all that over t. So that's the definite integral of the function 1 over x squared square root of 1 plus x squared dx between 1 and t. And now the last step, we go back to our definition of our improper integral. So here we go, boom. But now we know that the definite integral from 1 to t of 1 over x squared square root of 1 plus x squared can be replaced by the function that we just freshly computed. So this will become the limit as t goes to infinity of the square root of 2 minus the square root of 1 plus t squared. Now, sadly, the problem with this is if you plug in infinity right away, you're going to get, for the second term, a infinity over infinity. Normally, when we have infinity over infinity, we would maybe try hospital rule, but here we need to keep the dominating term. So here inside the square root, t squared is the one that dominates, and at the denominator, we have t. So I'm just going to keep t squared inside the square root and t down there. So this simplifies to the limit as t goes to infinity of square root of 2 minus the square root of t squared over t. By definition, the square root of t squared is actually the absolute value of t. So here we go. Poof. So we have the absolute value of t, but the way you're going to get rid of an absolute value, because t is going to infinity, we know the inside of the absolute value is a positive quantity. So inside here, we have a positive quantity. So we know the absolute value is going to do nothing for that question. So this will become the limit as t goes to infinity of t over t. Poof, here we go. And now t over t, that simplifies to a nice 1. So now we have the limit of square root of 2 minus 1. And that's just going to be equal to the square root of 2 minus 1. So here we go. Poof. So then our final conclusion, because our limit is a finite number, is that the improper integral from, oh, forgot my bounds here, from 1 to infinity of 1 over x squared square root of 1 plus x squared dx converges to the square root of 2 minus 1. All right, so big question. So here, make sure that you understand where the indefinite integral comes from. So the way I got my family of antiderivative, this question is not trivial. If I include the solution of step 1, this becomes a very long and complete question. So make sure you know this is good review for trig substitution. But once we have a primitive, the rest of the solution is the same. All right, for this section of improper integral of type 1 or type 1 improper integral, that's it. That's all. Bye-bye.